Hello, everyone. Thanks for coming to my presentation. So as introduced, today I'm going to be talking about leveraging GraphQL for continual learning in real-time ML systems. So before jumping into the talk, I'd like to discuss a quick agenda for the talk. So first, I'd like to begin with a small introduction to myself. Then I'll cover an introduction to machine learning, because how can us as engineers solve problems without understanding them in the first place? And finally, we'll jump into the meat of the talk, where we're going to be discussing how to set up real-time infrastructure and continual learning infrastructure utilizing GraphQL. And finally, we'll discuss the conclusions and what's next in this exciting field of engineering. So first, just a quick introduction on myself. So as you guys saw on the title slide, my name's Aryan Magoon. I'm a senior studying computer science and electrical engineering at the University of Virginia. I spent this last summer at Apple working on supporting multitasking features for iOS and iPadOS. And a lot of my previous experiences deal with building performant distributed infrastructures and novel ML architectures for various tasks. So now let's enter into our main talk, which is, we'll start with the introduction to machine learning and how it's used in industry. And just so I have an idea of who's in the room, can you please raise your hand if you use machine learning in production? All right, so for those of you that raised your hand, I hope this provides a quick refresher of topics. And for those of you that didn't, this will be a good basis for the rest of our conversation. So what exactly is machine learning? And although I know it seems like magic, I hate to burst your guys' bubble, it's not. Essentially, machine learning is an application of math and computer science that aims to build algorithms from data. In general, machine learning problems are split into two phases: training, where our algorithm will learn from data, and inferencing, where we're going to use our trained algorithm to make new predictions based on the data that we trained it with. And it's important for us as engineers to build proper infrastructure so that both of these stages are as efficient as they can be. And additionally, it's important to note that machine learning is a paradigm where systems are designed to act and make decisions based only on data-driven insights rather than explicit programming. And this is in complete opposition to software development, where we aim to anticipate every action and response. And finally, I'd like to mention that there's three general types of machine learning: supervised, unsupervised, and reinforcement learning. And before we can jump into exactly what these are, I'd like to take a snapshot of machine learning in production. So, as we've seen in the last couple of years with the evolution of machine learning techniques, an unprecedented amount of capital is being invested into machine learning by companies, governments, and schools. So, and this is corroborated, as we can see in the IBM AI Adoption Index. It states that 35% of companies that were surveyed currently use machine learning in production, and another 45% are working to integrate it. However, although we have many different types of machine learning and use cases, they're not necessarily used equally in production. So, as we can see in the graph provided by a 2020 paper written by researchers from Wageningen and Boccaccio University named Machine Learning Applications in Production Lines, they aim to learn about the state of the machine learning and what type of algorithms are dominant in top ML papers at the time. And as we can see in the graph above, supervised machine learning dominates industry applications, so it's going to be the main focus of our talk. We're going to discuss how to set up infrastructure for these type of problems. Now let's jump into exactly what supervised learning is. So, supervised learning is a form of machine learning in which we attempt to train a predictive function by providing our algorithm with training data, which consists of input-output pairs. Essentially, we're going to know the answer for every example in our training data set, and the model would be tasked with learning the relationships between the input, otherwise known as features, and the output or label by getting exposed to numerous examples in our training data. And finally, once trained, supervised model's performance is typically evaluated on a separate set of testing data, which contains unseen samples as well as the known labels. We can compare the labels the machine learning algorithm predicts compared to our true labels in order to get the accuracy. And in the end, the goal of our supervised learning algorithm is to make accurate predictions on new data. As we can see in the diagram provided by V7 Labs, our supervisor provides the training data set and the desired output or labels into our algorithm in our training phase on the left. And after training, we can feed it new data for processing and observe new outputs in our inference stage on the right. So in order to make sure that we understand supervised learning, I'm just going to give a couple of examples of supervised learning algorithms. So on the left, we have an app idea from our favorite developer on a TV show called Silicon Valley. And in this machine learning problem, we aim to basically classify if an image is a hot dog or not a hot dog. So in order to train our model, our input data would consist of images that would be hot dogs and not hot dogs, and with the corresponding labels of whether that image is a hot dog or not a hot dog. And then the end goal of the system is to essentially see new images and determine if they are hot dogs or not hot dogs. And in the example on the right, we have a more practical example of supervised learning where we are trying to classify the type of reviews that we are receiving on our app in order to learn what features developers need to prioritize fixing. In this machine learning problem, our input data would consist of customer reviews that we can collect from the App Store or otherwise, and we can label these with certain classifications as we see in the image. Some examples of these labels are like pricing complaints, maybe a positive feedback that we can avoid, and unresponsive UI. So, and the goal is to essentially take new reviews that we've never seen before and try to classify them. This will allow the team to easily count which features are receiving the most negative reviews and see which features we need to prioritize in fixing. And now that we know what supervised learning is, we can learn what's the most common way that supervised machine learning algorithms are served in the industry. So as we can see here, we use a sample machine learning architecture that's provided by Instacart in one of their engineering blogs. And this is a sample machine learning infrastructure that's predominant in industry known as batch prediction. So at its core, there's a backend service that'll log and store session events in a centralized data warehouse. This warehouse would act as a reservoir of information, storing data to train our machine learning model and storing them as features to make predictions on later. To predict using this data, our offline prediction platform will take our batch features provided in our data warehouse at scheduled periods and run our model through these features, producing predictions on them. And then we can store them in our intermediate prediction store as we see above. Now, when our backend service requests these predictions, we can swiftly retrieve these pre-computed results, ensuring a rapid and efficient response. These scheduled updates can be easily scheduled with cron jobs. So as we see, this type of prediction provides a number of benefits. We have scheduled processes for prediction, so we can compute them at scheduled times and aren't held to strict latency standards. Additionally, depending on the infrastructure, it might be more efficient on a per prediction basis rather than processing them individually, saving computational resources. But of course, in engineering, we know there isn't anything such as a free lunch, so why are batch predictions suboptimal in certain applications? So as stated in the Instacart blog, the engineers noted a number of deficiencies in this system that can be applied in general to the batch prediction paradigm. So the first is that using batch prediction paradigm can often serve outdated predictions. So as we've just discussed, these predictions are computed on a scheduled basis, but a lot can happen between these intervals. So let's just illustrate an example directly from Instacart. So let's just say every week I go onto Instacart just to buy potato chips. One week, let's just say I want to branch out, and this week I want to buy a soft drink. If the system solely relies on my historical data, I'd only see recommendations for potato chips, which is not what I currently desire. Another deficiency in the system is that it has some resource inefficiency. And I know I just mentioned that it might be more efficient on a per prediction basis, but it doesn't necessarily mean that we're using all of our predictions. So suppose Instacart computed predictions on a daily basis, but only 5% of their users actually logged on that day. We're still wasting 95% of our predictions. And then finally, the lack of up-to-date features can affect the prediction quality. So as another example that might be relevant to Instacart, imagine that Instacart uses an algorithm to optimally place delivery drivers near grocery stores. Without real-time updates on customer behavior and what they're looking at now, drivers might not be able to be positioned to ensure the quickest delivery times. So obviously, this leads us into the next portion of our talk, which is, we want to be able to take our users' data in real time and make decisions on it, which is how we're going to be setting up our real-time infrastructure. So obviously, the first step to this is obviously collecting our real-time data. And I know what a lot of you are thinking. Can we just do something like this? So as we can see in this, we can send the request directly to our model store from our application. But there's a number of issues that come along with doing this. Aside from the fact that the session data usually cannot be used for machine learning, it needs some sort of pre-processing, HTTP requests can overwhelm the model store server and make it hard to handle increased traffic. Additionally, if we're making synchronous requests, HTTP requests to the model, it can remain in an awaiting state until the model processes our inference, leading to perceived delays in the user experience. Additionally, direct HTTP requests lack inherent retry mechanisms and can introduce a single point of failure, risking data loss and system halts. And finally, there can be some model deployment issues when we want to update the model, and any redeployments may lead to service interruptions, leading to a decreased user experience. And after understanding the limitations of directly querying the ML models, it becomes clear we need a more robust solution, and that brings us to one of the many tools that we're going to introduce today. This is Apache Kafka, an open source distributed event streaming platform that has the ability to handle large amounts of data with extremely low latency. It works by storing data in topics, which are essentially ordered logs of data that we can publish and subscribe to. These logs are replicated across multiple servers known as brokers, giving us fault tolerance, and split into partitions, which is our main means of performing multi-threading, allow us to minimize our latency in the application while maximizing our throughput. And in the end, we're going to be using this tool along with GraphQL in order to collect the real-time features from our application. So here we can see the first piece of our infrastructure. Now our users are going to be interacting with our app through our usual GraphQL API, sending various queries and mutations to the server that can represent session data from our application that we need to collect. So things such as login requests, logout requests, navigation patterns, content interactions, shopping cart activities, etc. And within these queries and mutations, we can publish the necessary data into our Kafka topics, into our streaming transport for later processing. So now we have the real-time features, but we still want to be able to process them and make predictions on them. So first, we're just going to discuss a couple of tools that we're going to be using in order to do this. So the first of these tools is called Apache Flink, which is a highly scalable stream processing engine, which at its core is designed to process vast amounts of data in real time with incredible efficiency and low latency. Now, why is Flink important to our setup? And here's the connection. We're going to be using it to consume our Kafka streams containing the real-time data from our users. And we're going to be doing two things with it. First is we're going to be performing feature engineering on it. So as I mentioned earlier, usually the raw data from our application can't be used to directly inference our ML infrastructure or ML models. So we need to do that pre-processing step. And finally, the second thing it must do is store these features inside of a database that our machine learning model can later use to make predictions and serve back to the user. So in essence, Flink is serving as the bridge between our raw data from our application and features in our database, ensuring models have access to the freshest data. So now, I know we discussed storing it into a database, so now let's discuss the database that we're going to use. So the database that we're going to be used is called KSQLDB, which is a real-time event streaming database that's built directly on top of Kafka streams. It marries the best of stream processing with SQL-like querying for low learning curves for everybody involved. So using a conventional database to store our real-time features introduces massive latency into our applications. And in applications such as real-time ML applications that we are building, extra latency in our pipeline directly impacts the customer. So this is unacceptable. Some of the benefits of KSQLDB is that it provides lightning fast retrieval and storage, and that it's built directly on top of Kafka, thus it seamlessly integrates with our current infrastructure. We're going to be leveraging this for rapid storage and access in our application. So now that we've discussed these two tools, we can show how they fit in with our current infrastructure. So in this, we can see that our Kafka stream is consumed by our stream processing engine, Flink, which will perform the feature engineering and allow the data that's sent to us by Kafka to be used to inference our ML service. And we're going to be storing these features inside of our streaming database, KSQLDB, as we have just discussed. Additionally, this will be in-queuing a prediction request onto our ML service, which serves the model that we're trying to inference. So by using a queue instead of simply calling for the model to make the prediction, we can provide a number of benefits, including fault tolerance. So for example, if the model encounters an issue or needs to be restarted, the request in the queue can remain intact and processed once the service is back, meaning we don't have missed inferences. Additionally, we can have additional scalability. So if our queue becomes very long, we can choose to spin up more instances of our ML service to stick to those latency requirements as we were discussing before. So this encapsulates the infrastructure we use to process the real-time features that we receive from our Kafka data streams. So now finally, we can move on to our third and final step where the magic finally happens: inference and actually serving the predictions. So finally, as there are no more tools to discuss, we can just jump right into the final portion of the infrastructure chart, which is inferencing the model and serving the prediction. So in this step, once the inference request is dequeued from our ML service, we can actually begin to process it. With data that was passed along from Flink to the ML service, we can query the necessary features that we need to make the prediction. Once we query the current request and receive the necessary features, we can inference the ML model and receive a prediction. And now, how are we exactly going to serve this prediction back to our user? We'll have another Kafka topic opened in our ML service that we can publish to. And finally, in our GraphQL API, we can declare a subscriber that'll subscribe to the topic, and upon receiving the request, we can serve this prediction to the user by updating various fields pertaining to the prediction, such as various ML-powered menus, dashboards, notifications, and other interactive components. This ensures that the users benefit with the real-time predictions as fast as possible once we've generated them. Finally, now that we have a full view of the architecture that provides our real-time inference, we need to take note of the latency introduced from Flink. We want to do our feature engineering extremely efficiently, and additionally, we need to take care of the latency introduced by our ML model. Obviously, these are both very expensive processes, so we need to be ensuring that we're doing it as fast as possible in order to be serving our predictions as fast as possible. So now that we've ensured our model is getting the most up-to-date features, are we necessarily finished? And surprise, surprise, the answer is no. We're providing our model with updated features, but we still aren't doing anything to ensure our model quality over time. So how can we ensure our models remain accurate in a world of ever-changing data? So first, I'd like to discuss why we can't necessarily just use one model in production and why we need to update them. And the first is that over time, the nature of the data that we deal with can change. As we've shown in the introduction to machine learning, we train the model off of our input data. However, if the data from the model that the model is being inferenced on doesn't necessarily represent the distribution of the data that it was trained on, it can lead to suboptimal model performance, and a static model won't be able to account for these evolving patterns. Secondly, our machine learning model might need to introduce new labels. So going back to our second supervised learning example, let's just say we introduced a new feature and we want to be able to classify those. We don't have any labels, so we need to be able to use that. And last is continuous improvement. So as we collect more data, our models have an opportunity to learn and improve. In sectors where a slight competitive edge can make significant impacts, so think about maybe applications such as trading, continually refining models ensures that we can maintain that edge. So while a single model might serve us well for some time, the dynamic nature of data and business needs requires us to be agile and evolve our model as necessary. So now enters the concept of continual learning. But what exactly is continual learning? So continual learning is a method in which we can update our models statefully in production. And what we mean by statefully is instead of completely retraining our model from scratch, we can simply fine-tune it based on the new samples that we see rather than completely retraining it. And it's not necessarily about retraining after every sample as it may suggest. And you might be wondering, why don't we update the model with every single sample? And the answer is usually it's not worth it doing so. The computation cost of updating models with every sample becomes very costly, and our models don't degrade fast enough to necessitate that cost. And additionally, continually learning models have had some issues with a phenomenon known as catastrophic forgetting, where the model forgets the data that it was previously trained off of, instead favoring new data more. Thus, instead of retraining on every sample, it is based on a trigger. And this can be a number of things, such as data distribution shifts, the number of new samples collected, and in order to enable continual learning, we can split this up into 4 main steps, which is data collection, trigger, learning, and testing and deployment. So let's just jump straight into our first step, which is new data collection. So obviously, we need new data in order to train our model off of. So how are we going to get it? And luckily, as we have hopefully launched our initial model into production, we have our input features already stored for us in our streaming database. So instead, we can just add a new component to our infrastructure, a data lake such as Snowflake, et cetera. And on a scheduled basis, we can store the new data from our stream database into our data lake. This gives us our new input features. But as I mentioned earlier, for supervised learning algorithms, we need our output labels. So how can we get these? In some applications, we can collect feedback directly from the user, and this can be seen in some machine learning applications like ChatGPT. So for example, after you give it a prompt, you might be able to see a thumbs up or thumbs down. You can say how good the response is. Or additionally, depending on the type of machine learning, we might be able to generate implicit labels. So for example, let's just say we're running a recommendation engine. Then let's just say we recommend 2 pieces of content to a user, and let's just say the user interacts with 1 piece of content for 10 seconds versus 10 minutes. It might show the quality of the recommendation then. In addition, we might be able to just kick off manual labeling. Maybe we have a separate team in order to do that. And finally, although I won't go into this too much, we might be able to use machine learning, specifically unsupervised learning, to generate artificial labels. And as this is a proof of concept, we're just going to be assuming that we have the labels stored inside of our data lake already. So now that we have the data stored inside of our data lake, we can move on to triggering our model retraining. But first, we must introduce a new tool that we're going to be running the rest of our continual learning pipeline through. And this tool is known as Apache Airflow, which is a workflow orchestration tool that allows us to build computational workflows and pipelines programmatically. They function as a directed acyclic graph of tasks. And you can visualize it like a flowchart where each task can point to another, ensuring there's no looping or cyclical dependencies, which ensures error-free execution. And given its capabilities, we can use Airflow to employ a majority of our continual learning process. So the first step in our process is getting a trigger, and understanding when to update our model is very crucial, and that's where triggers come into play within our Airflow setup. So first, we're going to set up our Airflow directed acyclic graph to be executed at specific intervals. And to kick off the entire process, our initial task is our triggering task. When it is executed, it'll delve into our data lake and pull the recent batches of data. And once we have our data, we can assess if an update is truly required, performing various statistical tests if we have data distribution shift, determining if we have substantial amount of data or whatever the trigger is. And based on that decision point, one of 2 things can happen. Either a trigger is detected and we can move on to model retraining, or we don't have a trigger yet and we can just wait for the next scheduled check. And on the side, you can see this visualized. So the next step is model retraining. And if we have a trigger, we can move on to model retraining. But first, we need to introduce the very last tool of this process, MLflow. MLflow is a platform that manages the machine learning lifecycle. And the main features of MLflow is our model registry, which is a central hub which records all of our models, making it easy to access and manage them. There's experiments, which allow us to run and track different model experiments, such as training or evaluating. And finally, it's extremely good at storing artifacts of our machine learning models, which is very crucial for the continual learning process because the need for meticulous record keeping intensifies. We essentially want to keep track of which model was fine-tuned from which predecessor, along with data versioning to see which data the model is fine-tuned with. And keeping track of this metadata allows us data science teams to take a step back just in case anything happens with our model retraining. Perhaps we're suffering from the catastrophic forgetting that I mentioned before. So now we can take a step back again and look at our system thus far. We can finally see the branches of our triggering task that will either trigger a new MLflow experiment, which will pull the data, the appropriate model, encapsulate all of the metadata as I've just described, and we can begin the experiment, or we can simply do nothing. And finally, once we have a new model trained, we can go into our final stage, which is testing and deployment. So can we just serve this model right out of the gate? And maybe the section header for this was a bit obvious, but the answer is no. Just as with regular software, machine learning models need to be tested rigorously before they reach production. So the first step of our evaluation process is offline evaluation. So as we've stated in our supervised learning section, we can just section off a portion of our data lake and identify that as our testing data. And we can just kick off another MLflow experiment in order to verify the accuracy of the models or other metrics such as F1 score or anything like that. And we can see this in our directed acyclic graph. And now we're ready to move forward to bringing this model into production. So if our new model performs better than our current production model on static analysis, then we can move on to this new step. But before we can fully transition to this new model that we've trained, we need to test our model more on real online scenarios. Essentially, we need to understand that we're retraining these models in order to try to perform better in these environments, and only testing on static data is not enough. We want to be able to use real-world feedback. An online evaluation will expose this model to real-world scenarios, which captures nuances that aren't necessarily available in static data sets for offline evaluation. And additionally, we can ensure that the model will handle the volume of live traffic and will scale appropriately under demand. In order to do this, we can utilize federated GraphQL to implement BlueGreen deployments to gradually integrate our model to our consumers. But first, let's discuss what BlueGreen deployment is. So think about BlueGreen deployment as having two separate infrastructures for our model, blue and green. And at any one time, the blue environment is actively serving our users, while our green environment is on standby. When we have a new version of our model after our training experiment, after we've performed our offline evaluation, we can deploy it onto our green environment and perform various other activities to be able to perform predictions, such as maybe syncing our stream database so that maybe either can serve predictions. And once deployed, the green environment can be thoroughly tested without affecting the live blue environment. And once we're satisfied with the performance in the green environment, we can start redirecting traffic from blue to green, which should be a smooth shift for our users. And in case of unforeseen issues, we can simply redirect all the traffic back to our blue environment, take a step back, and reevaluate. So as we evolve our infrastructure, let's discuss how we're going to evolve our infrastructure to support now federated GraphQL. So of course, one of the shifts we're making is transitioning from our GraphQL monolith to a Supergraph. This transition fundamentally changes how we manage and deploy our real-time features. So instead of sending all of our real-time features directly through mutations now in our monolithic system, the Supergraph allows us to break down and serve the models as various subgraphs. And of course, the model subgraph isn't the actual ML model, but rather the interface to it, describing various mutations and queries that'll trigger prediction requests, as we have seen in the real-time infrastructure. Then we can serve a load balancer as a subgraph in the middle, and any request to our subgraph, or ML, can instead be routed to our load balancer. In our load balancer, we can enable sticky sessions to ensure that a specified percentage of user sessions are directed to the blue environment, while the remaining sessions are routed to our new green environment. So now we can see this infrastructure ahead. So moving forward with this, we can look at the diagram, which now shows a simplified version of our new serving infrastructure. So starting on the left, we now have our GraphQL router, which is the primary entry point for all GraphQL requests. And once a request arrives at the router, it's directed to the load balancer, which we can serve as a subgraph as explained above. This component is responsible for determining where incoming requests should be directed, particularly when it comes to ML services. And finally, to the right, we can think about our blue-green environments. As we can see in these blue-green environments, we have identical real-time deployments, as we've discussed in the previous section, with a subgraph in order to log our events, Flink in order to process these events, a KSQL DB instance to store these events, and an ML service to be able to run our predictions. And in the end, as we can see to the right, our legacy ML service is represented in blue, which is our current ML service. It's been thoroughly tested and is currently handling a majority of our traffic. Our potentially improved green service that we have now deployed is now in our testing phase and receives a small portion of the traffic, allowing us to dynamically evaluate its performance in real-world conditions. The percentages of traffic directed to each service can be dynamically adjusted, allowing us to slowly transition requests from our blue service to our green service. And once we have determined that our blue service is performing, our green service, sorry, is performing well, we can eventually fully transition into our green service, which will then become our new blue service when we attempt to retrain the model again. So there's a number of benefits that come with deploying our models like this. And the first is that it supports model changes. So we can choose when in our different queries and mutations and different subgraphs to choose to send different types of data, which allows us to experiment with different models rather than retraining the same model. Additionally, it provides built-in fault tolerance and low downtime. As we are serving the model in a blue-green infrastructure where we update our models, presumably our green environment is completely outdated and isn't receiving a single request. So we can easily deploy into our green infrastructure without it hindering the user. And additionally, we have built-in fault tolerance. So again, as I mentioned, if anything goes wrong with our new model, we can simply route all requests back to our blue environment and take a step back. And yeah. Finally, it allows for deployment flexibility across teams. So by not unifying the platform, we allow for various teams to work and deploy separately on various types of problems that they're working on. And this ensures that teams don't have to work together in lockstep when making changes to their individual models. Instead, they can just work on serving their individual blue-green deployments. So finally, we can see the full infrastructure for this diagram, or for this problem, sorry, and we have the last portion of our Airflow DAG, which can deploy the model onto our green instance and route the predictions as described before. So finally, let's jump into the conclusions of the talk. So as we've seen in our real-time section, we can use GraphQL mutations and queries to track user session data, which triggers model inferencing. And we can deliver this content right back to the user by using Kafka and GraphQL subscriptions, ensuring the real-time predictions reach the user as fast as possible. And by using federation, it allows us to decouple our architecture and allows for blue-green deployments, which ensures minimal downtime and testing in a continually learning environment. And finally, as an aside, we didn't mention this, but by adding a GraphQL API, we can create queries for our data scientists to pull both streaming and batch data directly into their notebooks, allowing our data science teams to move faster. So now comes next steps. And a lot of people ask me about the next steps. And the truth is, we truly don't know. A lot of the tools that I discussed here were very premature and unable to be used in industry just a few years ago. So truly, with this much capital being in machine learning, we don't know exactly what tools are going to come out of it. However, I do believe that GraphQL has an important place in the future of MLOps. So if you'd like to look at my references for the talk, you can take a picture of this. And I'd recommend taking a picture of it because we're going to have another QR code to scan soon. And I'd really appreciate any feedback. This is the first talk I've given at such a big conference, so I'd really appreciate any feedback you guys have. And finally, if you guys have any questions, I'd be happy to answer them. Feel free to email me, or I have a topic table very soon. So if you guys would like to have any questions about the talk or general questions about machine learning or MLOps, I'd be really happy to answer them. Thank you so much.